So good morning, good evening, good afternoon, everyone. I'm a third-year PhD student working at the University of Bordeaux in France. And today I'm going to talk about field measurements and modeling of nearshore currents at a high-energy, geologically constrained beach that is actually shown in the background picture. So why do we study such circulations? Well, because it plays a key role on the hydrodynamic processes along wave-dominated coastlines. And these processes include sediment exchanges between the surf zone and the offshore. It is also a beach safety hazard with rip currents potentially exposing a bunch of swimmers offshore. And also during extreme wave event, it can induce extreme coastal erosion. Along open sandy beaches, the circulation patterns are relatively well known with alongshore currents under oblique waves and a circulation cell system under shore normal waves. But along beaches with strong geological inheritance, these patterns may be much more complex. And a typical geologically constrained beach are on-bait beaches that are closed by two headlands at the extremities. And within this system, the most common circulation patterns are headland rips that are offshore directed currents flowing along a physical frontier, such as an headland or dikes or groins. And these rips are forced by two different mechanisms that depends on the wave angle of incidence. So when the waves are coming this way, the presence of the frontier will create a wave shadow area here, which will induce an alongshore variation in wave energy dissipation and in turn create a circulation in this way with the shadow rip flowing against the frontier. On the other way around, the breaking of the oblique weight here will create an alongshore current flowing against along the beach that is further deflected seaward by the frontier here and creating a deflection rip along the frontier. So what are the existing Headland rip studies? Well, there have been some modeling done along idealized on-bait beaches. A couple of in-situ hydrodynamic measurements have been collected, but just under low energetic and low varying wave conditions. There are also quite a lot of morphological evolution studies of on-bait beaches, especially under extreme wave events. But very few or none of these studies are associated with a comprehensive hydrodynamic in-situ datasets. So that's why we need such datasets. And that brings me to a 3-week field experiment that we performed at one of Anglais beaches in October 2018. The location of the field site is shown on the left panel here. The field site is just located close to this headland here, and the bathymetry and topography are shown on the right panel here. So these include a 500-meter long headlands that is bordered by rocks that can be emerged around low tide, and also a submerged reef here. And to measure waves and velocity, we deployed 4 IDCPs, which locations are shown with the colored points here. Also, we deployed 4 times drifter that allowed to measure Lagrangian surface velocities. And also we had 1 fixed and 1 non-fixed camera that allowed to monitor the wave-induced circulations within the area of interest, but these are out of scope of the presentation. We have also implemented an XBeach model that solved the coupled 2D horizontal XBeach equations for wave propagation and flow, and also sediment transport and bottom changes, but these models were turned off as we mainly focus on the hydrodynamics here. We used the surf-beat approach that allows to resolve the hydrodynamics at the wave group scale, but in a short wave average manner. The domain that was implemented is a 10K in the longshore times 4K in the cross-shore. That is centered at the field site here, where the mesh size is where the mesh resolution is much finer. with a 5-meter mesh size in both distances. So that the offshore wave condition and tidal levels, well, these covered a really large spectrum over the during the October 2018, especially there were several energetic wave events where the significant wave height exceeded well beyond 2 meters. And also very oblique wave and short normal wave event. But here we mainly focus on two deflection events, D1 and D2, where the wave angle of incidence is positive, which means that waves are coming this way, and a long-shore current is expected to be deflected seaward and creating a deflection reef here. So we refer D1 to the low energy event and D2 to the high energy event. So let us compare the measure and the model. First, let's have a look at the waves, the significant wave height of the gravity waves in red and the long wave in blue for both events at each instrument. So in short, the model is able to reproduce quite well the temporal evolution of these significant wave height with roughly 0.8 correlation coefficient for both significant wave height. In terms of currents, we show here the 5-minute time average velocities. So again, in short, the model is able to reproduce quite well the tidal modulation and the order of magnitude of the mean flow. But now we mainly focus on the energetic event that is shown on the right panel here. If we focus on the low tide of this event, here we show on the left panels here the temporal evolution of the velocity magnitude for both the model in black and the measure in blue at both the offshore instrument here, SIG1, and the onshore instrument here in blue. So once again, the mean flow and the tidal modulation are well represented, but also, most importantly, at the offshore location, the model is able to reproduce quite well the very intense reef that flows offshore, and also the really strong, intense, very low frequency fluctuation. Here we can see the 4 peaks that are both modeled and measured, roughly 1 hour spaced. And in terms of magnitude spectrum on the right, the energy levels within the very low frequency band are really well reproduced by XBeach, both offshore and onshore. So if we have a look at the animation of the currents, we see the longshore current here that is further deflected by the headland offshore. In short, the first two main observations that we see here is that the southern width is strongly correlated with the width of the deflection reef here, and also the mean flow of the next embayment here strongly influence the deflection pattern, at least the reef head here. If we average the pattern over low tide on the left and high tide on the right, we clearly see that the deflection pattern is strongly tidally modulated. In short, the southern width, the larger the southern, the larger the deflection reef. And also the longshore current is fully deflected regardless of the southern width, which was unexpected, especially at low tide, where the southern length width is of the same order as the length of the headland. The longshore current is still fully deflected, and this is because the mean flow coming from the adjacent embayment deviates the rip head and allows him to be fully deflected and extends well beyond the tip of the headland. And at high tide, the mean flow coming from the next embayment has a relatively low influence on the deflection patterns. So we have, let us say, the most expected and classic deflection rip pattern. So if we have a look at the standard deviation of the 5-minute time average the velocities, which characterize the VLF fluctuation intensity, we see that the patterns are also tidally modulated with less intense VLF fluctuations at high tide than at low tide. And at this time, the rip fluctuates much more close to the headlands here, and the VLF intensity decrease as we go further offshore. So to conclude this presentation, we have presented the first extensive dataset of hydrodynamics along a geologically constrained beach. We have implemented an XBeach model that is found to be able to reproduce quite well the deflection rip patterns, which include the tidal modulation of Eulerian velocities, but also the fluctuations of intensities within the very low frequency band. We have shown that the longshore current is fully deflected regardless of the sail zone width. And that is because there are strong, important hydrodynamic exchanges between both embayments. So about the ongoing work and the still pending issues, we are currently investigating the driving mechanism of the VLF fluctuation. Also, what about measurements of the hydrodynamics along the adjacent embayment to further study and investigate the exchanges and, let us say, communications between both embayments? And also, what about the circulation patterns under different configurations, that is, shore normal waves or shadowed configuration, which are shown on the right panel here. So thank you for your attention, and do not hesitate if you have any questions. Thank you.